All right, we only got like 5 live streams left before we hit the end of the semester, so we are in the home stretch, and hopefully you're going to find the alkynes and the ether sections incredibly easy. They were actually kind of refreshing to write because honestly, when I made the notes, I just copied and pasted a lot of the stuff from the alkenes and just kind of stuck it in there. I do want to thank most of y'all for catching that discussion board on 423 for today. There's actually a mistake. Number the compound right before you finish the loop is not supposed to be the dibromo complex. It's supposed to be the Cl complex, but I think through process of elimination, a lot of you figured out I meant to put the chloride. So the compound, you've got that loop. Compound number 5 is not supposed to be this. You can tell when I copied and pasted the figure, I accidentally copied and pasted the one that was up here. It's really supposed to be this or this. It doesn't matter with the HCl addition, because with the HCl addition, neither of those are particularly favored carbons. It's probably going to favor this one more likely just because of steric hindrance, but you're kind of like talking like a 60-40 ratio. Like it's not going to be a substantial difference. But again, process of elimination, you probably noticed that you only had the HCl left over, which would have been in the addition reagent, and then you had the alkoxide left over, and the alkoxide would have gotten you back to the alkene starting compound. So good job catching that. Big announcement for most of y'all. I have actually found out today that I am teaching Orgo 2 in the fall. So if you need Orgo 2 or want to take Orgo 2 and you're here this fall, I am actually teaching it. For right now, we are assuming it is online until we hear otherwise. Now, those of you who might be doing something like attending college in this fall, perhaps UNCW, might need to check to see if any of the schools are actually opening this fall. Big thing is that a lot of the universities are still kind of on the fence about whether or not they're going to open this fall. Financially, they have good reason to, but they don't want to deal with an outbreak of COVID-19 because they reopened. So some of you, even though you may technically be starting the fall, your semester is not going to start until the spring, so you're still going to be around. So again, check organic sections typically don't fill up entirely. This class was kind of an exception. So if you need to take organic 2 and your college is not going to be open this fall, might be a good idea to go ahead and just take it at Wake Tech. Come here. There you go. Sit down, take your nap. I don't know, questions. Alkynes must be really easy. I mean, they kind of are, right? Like, the only weird ones are when you have, like, an alkene with an alkyne, but it's kind of esoteric, and honestly, it's not going to be on the final. It's mostly kind of prepping you depending on how you take for Orgo 2. The lab practical question thing due. I think it is due. Actually, I can check right now. I shouldn't be thinking. I can look up on Blackboard. So lab report 2. Is due May 1st. So it looks like it's due Friday of next week. Probably gave you that due date just for my own sanity. I do actually need to go through and read and grade these, but definitely May 1st. Solvolysis. So let me make sure I'm looking up the right reaction for you. So when you say solvolysis, you're referring to the water addition to alkynes, if I'm correct in that statement? Solvolysis is the alkene homework. Okay, that's why I'm struggling with it. Let me bring it up. Actually, let me bring up the homework, because apparently I didn't discuss it in the notes either. You would perchance know the question number associated with solvolysis, would you? So I've got it on my end, but I'm going to try to find it. Of course. The problem is solvolysis can refer to a lot of things. So this is why I can't really answer your question. It refers to a lot of things, and I'm not recalling. I know what I think solvolysis is, but I'm pretty sure that's not what your book says solvolysis. So for me, solvolysis is the effect the solvent has on the actual stability of the intermediates and how the solvent plays a role in creating stability. I'm pretty sure that's not actually what, I think yours is referring more to the reaction of the solvent with the organic compound. So plan here is to look at the problem and see what the question's asking, and from there I can explain it to you. But this is definitely mine not having a background in organic chemistry showing through. Like, it needs something different in other fields. Ozonide, how do you work with those? Ozonide. You'd have a question number for that one, would you? Because it looks like, just quickly what I'm seeing is ozonide is just formed as an intermediate of the ozonolysis reaction. Number 43 for the solvolysis. So the question I'm seeing for number 43 is secondary butyl bromide and methanol. So secondary butyl bromide, the reaction with methanol. What on earth? This apparently was not the question it showed me when I picked this question as a problem. Okay, so solvolysis is the reaction of, okay. So solvolysis is the reaction where your solvent, okay. So for solvolysis, your solvent is also the reactant. So, okay, feel a little bit better about that one. So when it comes to solvolysis, what's happening is that the solvent itself is actually serving as a reactant. So typically when we have a reaction, we think of our reactant separate from the medium that it's in. So when we run a reaction in air, so we mix two things in air, we assume the air is not involved. If we have an aqueous reaction, something dissolved in water and something else dissolved in water, we typically ignore the water. In this case, we actually have the solvent itself forming having a reaction. So when it comes to the solvolysis reaction, it's basically saying, what if your solvent was also a reactant? And in this case, it's just nucleophilic substitution. So you have your oxygen attacking the carbon underneath the bromine, giving up the electrons to the bromine, and you end up with your ether. So solvolysis is just really a fancy way of saying that the solvent is involved in the reaction. It is also what's participating in the reaction as well. Major advantage of solvolysis reactions, these are all equilibrium type reactions. Because of that, when they react, it's going to drive it really far forward. So if you have water as a reactant, an reversible reactant, and your solvent is water, you're pretty much guaranteed to drive everything to the product. Now, in terms of the ozonide, last three. So 88 was just addition. Hold on. Oh, I hate you, organic chemistry with a passion. So, ozonide. This has got to be a horribly stupid way of naming these compounds. So an ozonide is any compound with the form RO3 minus 1. So, simplest ozonide is ozone with a -1, which doesn't really exist. A more common ozonide is something like this, which is a peroxy acid. So when we say we are reacting with an ozonide, what we're saying is that we're really reacting with a peroxy acid. And the reaction of any peroxy acid with an alkene is an epoxide. And I say that's horribly stupid because if you say ozonide, you would assume this means ozone, and we know the ozonolysis reaction. You would also assume that since we're deriving this up off of peroxy acid, we would per se it's like a peroxyate or something that we would associate with an organic acid which has reacted away its hydrogen. But all an ozonide is a peroxy acid under basic conditions which has lost its hydrogen. So it's going to act just like a peroxide. But those would be good things to add to the notes. So thank you. But yeah, I don't know why you would call it an ozonide. It's not ozone. It doesn't look like ozone. Like, that's not how we name organic acids that have lost their acid. Like, we call them oxalates. So this would be a peroxalate. Yeah, sorry for that editorial. It's like ozonide. I have no idea what that is. Makes sense. I got really good questions today, actually. Thank you. Because the weird thing is that I looked through questions 88, 89, and 90, and on the version I just looked at, there's no reference to the ozonides. So I'm guessing it's somewhere in. You all are basically getting slightly different homeworks because it's drawing from a pool of questions for each of your particular homeworks. So my guess is ozonide shows up somewhere in that pool. Who knows? So Terry, I'm hoping that answered your question. Really? No one figured out? Yeah, that's true. None of you figured it out. Well, you've made this compound. And you got a whole bunch of it floating around, right? So what type of alkene is this? I'll give you about 20, 30 seconds to respond. Unfortunately, this is one of those, like, once you figure out, I was like, oh, that's what happened. And I know because I actually had to reverse the synthesis. So when I was in grad school, I used to have to work with a compound that you had to remake it. And we'll talk about why in just a few seconds, why I had to remake it. But basically, you bought it in a bottle, and then you had to decompose it into the starting compound that you were actually interested in. But yeah, what type of compound is this? It's diene. And we got a whole bunch of it floating around. So what we can do is we can go Diels-Alder. And so we've got a 6-membered ring, and it's carbon 1, 2, 3, 4, 2, 3, 4, alpha, beta, alpha, beta. So coming off carbon 1 and 4, these are bridged. And then alpha, beta. we're going to get this component. And we've still got more diene floating around. So this diene can subsequently react with this part and react with this part. And we keep forming these successive reactions. And so this is the thing that the book doesn't tell you about, and it's incredibly painful to work with in the lab. Diels-Alder is not this like short, shiny reaction. What you end up creating is another alkene which can continue to work with your diene. And so in the case of the synthesis, you're going to get this big wad of wax in the bottom that's just basically this enormous conjugated Diels-Alder product if you're not careful. So with Diels-Alder, you have to keep the concentrations low or you'll get a lot of self-reactions. But yeah, the end product, and that's why I told you not to name it, just talk about the reaction that generates it. It's Diels-Alder. It will Diels-Alder with itself and create this wax paraffin at the bottom. And yeah, the compound I worked with in grad school, it was a compound that underwent Diels-Alder with itself. So when you bought it, it was just one wad. You had to stick it in a reactor and warm it up, and that would break the rings down, so it reversed the Diels-Alder process. And then you would recover the starting precursor, pull off what you needed, react it, and then stuck it back in the fridge knowing it was going to be... Yeah, like it's one of those, like, you see what the answer is, you're like, it makes so much sense. It's like, yeah, it's kind of something that the book doesn't really discuss about in terms of practical chemistry. Like, a diene is still an alkene. Dienes are less likely to react with each other, but they still will do it. So if you were to buy this 1,3 methyl cyclohexadiene, it's not going to be 1,3 methyl cyclohexadiene. It's going to be a big wad of Diels-Alder products that you're going to have to break down to get back to the starting compound. Now, mercifully, typically a diene is easy to break down, but yeah, it really does reactions with itself all the time. Otherwise, you have to buy it in really low concentrations, which creates issues of shipping and cost and safety. And you hoping it's in the solvent that would be useful for you to work with. That's also why I'm an extra credit, right? Like, it's just kind of a little clever thought experiment. Like, and nonsense like this happens in the real world all the time. My favorite one was at the national lab I worked at, and they told me the story about the grad student who had, and this is the correct thing to do, they had used glycerin to lube up all the connections in their glassware because they were having to feed it through a lot of rubber stoppers. And they flowed nitric acid through their reactor after they did it. Well, the thing is that nitric acid plus glycerin is nitroglycerin, and they had ended up making a ton of nitroglycerin inside their setup, and it blew up. So it actually, luckily, no one was there, and the fume hood did its job. But yeah, it's little things like this you just don't consider practical in the world. Another one we had, most dangerous lab I ever worked in, they mixed nitric acid with ethanol, and this makes an explosive gas and shock-sensitive explosive liquid. So if you shake it, it goes off. Luckily, there was enough water to decompose both products, but sadly, it wasn't the grad student's fault. His mentor was doing this for years, and no one caught on to the fact that this was an explosive that they were making. Also, full disclosure, organic textbooks have gotten less cool through the years, so the graphics have gotten way better and the explanations have gotten better. My version of Carey actually explains ethers and esters by talking about how to make heroin from morphine. I don't think that's in the new version of Carey. In fact, the older versions of Carey even talked about how to make plastic explosives, how to make certain types of, truly dangerous compounds. And they've kind of like backed away from that, saying, well, maybe we shouldn't be teaching students how to do that because the internet totally isn't a thing that tells you how to do this if you have a basic background in organic chemistry. But yeah, organic textbooks used to teach you this stuff because they're like, well, you need to know this, right? Like, don't blow yourself up in the lab. Well, we don't want people making it intentionally. Well, it's more dangerous when they make it unintentionally, right? But anyway, yeah, your version of the textbook is nowhere near as cool as the 3rd edition or like my version. But it's kind of like also like falling off. Like, it's not mine's awesome. It's just there's some things in there you really scratch your head like, was this the best example of an ether you could think of? Here's how you make heroin. I mean, it makes a ton of sense. I understand freebasing heroin now, but Yeah, like I would love to give a synthesis challenge problem in Orgo 2 where you had to make cocaine from scratch. Like, it's actually a very interesting molecule. There would be a lot of little nuances with that synthesis. You also would appreciate why natural cocaine is so much cheaper and easier to make than synthetic cocaine. But cocaine itself is actually, there would be a lot of tricks involved in trying to keep that thing from make that thing react, because there's amines, and amines are super reactive. They're great leaving groups, and because of that, you'd have to do a good job of protecting it. You've got an ester, so you need to make sure the esters point in the right direction. There's a lot of cool things that would be involved in that synthesis. So that would actually be a good, like, Chem 252, bring it all together. How do you make cocaine from scratch? Oh, and as a note for any of you who've didn't hear at the beginning, I am teaching Orgo 2 this fall. It's finally showed up on my course list now. So full disclosure, we're probably going to be online this fall. They've told us to brace for that, but it is there. So if you need to take Organic 2, particularly if you're attending a four-year university and they're not going to be open this fall, I'd recommend going ahead and taking it this fall. You're still going to have the same growing pains we're having this semester where notes aren't quite complete, the keys kind of have issues with them, but it's me, or I think Dixit is teaching it up on North. They're going to both be online, though. We're hoping they don't go through with their painfully bad suggestion of going to CETIC courses halfway through the semester. We just don't want to do that. Also, I assume you all have seen the announcement about the final exam. Your alkyne ether homework is going to be due the Monday of exams. I think I said the Monday at midnight, just so you have that extra bit of time. That's going to be 70% of your final exam grade. The remaining 30% is going to be 30 multiple choice questions, sweeping all the way back from first day of material up until alkenes. With a cycloalkene, it's going to be, so ozonolysis of a cycloalkene, it's actually, in my opinion, one of the easier ones to deal with. So with ozonolysis, just cut a line through your double bonds and put oxygens between them. So we have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. Double bond, and we just replace it with an O. And this would be true for any ring. Just count the number of carbons, draw out your chain. Your alkenes are going to become aldehydes or ketones depending on what they're connected on. And then I can see it, but if you can't see it, let's say we did this. Number your carbons. So let's say I had this compound. And I'm going to go 1, 2, 3, 4, 5, 6. 6 has a methyl, 3 has a methyl, and 2 has a methyl. So if it's a really well substituted cycloalkane, number your carbons, draw the backbone because the carbon ring is going to open up. Put your ketones or aldehydes in the correct places, and then put all your branches on it. But yeah, in my opinion, this is actually a lot easier than working with the linear ones. Just because the linear ones, you gotta make sure you didn't draw the same product twice. There's only one product with a ring. It's the opened linear chain form. Ozonlysis with a cycloalkene. Let's see. I know it's a weird intermediate. Okay. Yeah, coming back to me now. So in terms of your actual intermediate, and we'll make this a substituted alkene just to make it a little bit easier to see. Oops, there we go. You're going to get a tack. You're just going to basically form a 6-membered ring when you do, or a 5-membered ring. So the ozone adds to the alkene to give you a 5-membered ring. So there's your starting alkene. This would be your intermediate, which is the 5-membered oxo ring. This is going to further decompose back into your aldehydes and ketones. If you want the full mechanism, it's worked out in the online notes. I don't see a lot of merit to seeing the mechanism because there's no stereospecificity. You end up forming a trigonoplanar carbon anyway. So the bigger picture is the more important thing here. The lab discussion board, what were the 3 products produced after adding sulfuric acid? The low weights elements threw me off. So if I'm thinking about it right, ultimately you were supposed to form this complex. And ideally what you're doing is a double elimination, but you can get the single elimination. So the full double elimination will get you this compound here. So C7, 14 minus 6. That seems really low. 1, 2, 3, 6. Oh, it is 8. 72, 84. This would be 92 AMU. But you can also get the elimination product, single elimination products as well. So you can get the elimination of the alcohol, and you can get the elimination of the bromide. Now, these will probably be minority products, particularly this one will be a minority product. If we add back 17, that'll give us 109. If we add back 79, 89, 80.9. Don't tell me I put up the wrong mass specs. I mean, it wouldn't surprise me, but... Okay. Oh, looks like I put up the right ones. Looks like I flipped them. But yeah, they're there. So I'll share my screen with you. So this complex here clocking in about 90, that would have been the diene, which is what we were trying to get at. This one down here, there's a little peak at about 162. That would have been your single elimination with the alcohol. That would have been the 1-methyl, 6-bromo, 1 alkene. And then your lower one here with the 75 point, that might actually be incorrect. So your 75, 80. I think that the last one might actually be incorrect. So yeah, let me go update that for the discussion boards. So I do apologize for that one. But yeah, the first two are definitely correct. So the first mass spec was this complex here, which would have been really light. The second one is correctly assigned to this one. This should have been the third complex with the alcohol, but it looks like I signed the wrong one. So I may have done, honestly, what it looks like is I left off the methyl group when I did the mass specs. But yeah, definitely the first two are correct. Yeah, you're welcome. And fun fact, I couldn't find an IR for the brominated. So in the first reactants, you could have formed the alcohol, the dibromo, and this actual complex here. I couldn't find one for the alcohol with the bromine. So those are actually the same spectrum. Copy and paste it twice because I figured most of y'all wouldn't notice anyway. But yeah, I couldn't actually find an IR for this compound, so I just took the IR for this compound, knowing that you can't really see the bromides in the IR anyway. Can you perform metathesis with a cycloalkene? Yes, most definitely. In fact, this gives rise to one of the most famous uses of it, which is ring opening metathesis polymerization. So if we have something like cyclohexene, that won't work. And we do something like the Grubbs catalyst. Basically, we cleave it there. Now we have the option of doing something like ethylene or another alkene, or we can just do it with itself. And what we'll get, 1, 2, 3, 4, 5, 6, is this unit here. So we would get a 1 polyhexene polymer. And we can do this with any alkene we want. And basically, you can just create the cycloalkenes you want, polymerize them with themselves, and create unique polymers. There are ways to do this without metathesis. They are very synthetically involved. This is kind of a one-pot synthesis that pretty much guarantees you that you're going to get exactly what you want. Yes, you can 100%, if it's an alkene, you can 100% perform metathesis on it. Yeah, you're welcome. You're welcome. Yeah, we've got, again, I think alkynes and ethers are a good way to end this course. They're pretty easy to learn. They're just alkenes to the extreme. That's it. And because they are linear molecules, and when you react them away, you basically can't get chiral centers if you get rid of one of them. And typically, if you get rid of both double bonds, or get rid of both those pi bonds, you end up forming achiral molecules. We simplify a lot of the naming of the products. Now, next week's lab discussion board is going to focus on any questions you have about the practical. It's going to list out in the discussion board what specific topics are going to be covered. So there's going to be a question about, and it's going to tell you this question about this, question about this, question about this. So next week's discussion board is very much your opportunity to say, hey, could you clarify this concept? Could you clarify this concept? So again, the discussion board next week is just more meant for you to get feedback on what's expected of you. And then you're going to take the practical online. It's, I think, fill in the blank, multiple choice. It's a blend of questions. And 8 questions plus 1 extra credit question. Enjoy the fact my first semester teaching this course, which is the only reason you're getting extra credit to kind of compensate for, shortcomings in the material. Orgo 1 this fall will not be getting that. So, yeah, enjoy being one of the few classes that's ever gotten, more than 1 extra credit point from me. All right, if y'all don't really have any questions, like, we can finish up early. I mean, you had your test earlier this week, so yeah, I probably really haven't had time to start studying the new material. You know, like I said, this should not be hard material. I've intentionally front loaded the semester to make it get successively easier. All right. So there's 3 people watching right now: Terry, Hannah, and guessing Nicole's the 3rd one. So if you're all good, what we'll do is we'll sign off today. We'll be back Tuesday. Please ask any questions you have, and yeah, hopefully I'll see some of y'all again this fall, either online or physically see it in Oreo 2. So take care.